We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are Wicked Inventions. Coming up, pneumatic drills. We reveal the link from breaking rocks to air-powered drilling. Downforce. We find out why a wing can make a racing car fly round a track. Motorbike helmet. From leather cap to a famous death, the fascinating story behind this motorbike riding safety essential. We reveal the surprising science and amazing manufacture behind these wicked inventions. Today, pneumatic drills are used in homes and construction sites around the world. But just how was this wicked invention introduced?
So the pneumatic drill was first proposed, or the idea for some kind of drill like that, in around the 1840s. Now at this time, excavation, tunnelling, building was becoming quite a necessity of man.
During early excavations in tunnels, there seemed to be a continuous problem of falling rock and other debris, which created a demand for better safety.
So the first proposal was by a chap called Burton, who proposed the idea of a drill which could be powered by compressed air. It was a few years later, though, in 1848, when a guy called Couch from Philadelphia created the first patented idea for the pneumatic drill.
This model consisted of a steam-powered engine. However, this idea was only experimental. This prototype had the main drill operating through the steam engine itself. On the first use of this drill, the working piston snagged on the drill, hurling the whole machine against a rock face, causing extensive damage. From this, Couch's assistant, Joseph W. Fowle, then filed a patent for his own design.
So Couch's assistant, actually, Fowle, went back to the drawing board and worked out how the pneumatic drill could work. So his version was to fit the drill bit to the steam cylinder itself, which would give it the perfect amount of pressure. So in the 1850s, you have the first pneumatic drill built and created.
The turn of the 20th century saw many companies working hard to develop their power tools that would make excavation easier and safer than ever before.
Essentially, the function it performed in 1850 is the function it still performs today. It's a safer, more controlled way for excavation.
Compressed air is still used as a power source for many tools today, made by companies such as Chicago Pneumatics. But just how do they create their handy tool? Everyone needs a trusty tool to help them out, and there are thousands of different types of tools available. Based in Hungary, Chicago Pneumatics make a lot of different tools, including a pneumatic screwdriver.
Well, at Chicago Pneumatics, we've been producing screwdrivers for more than 10 years, and in this factory for actually almost 9 years.
The first step is to make sure all the incoming components are of sufficient quality. Around a third of all parts are checked using some of the thousands of tools and gauges available. Some checks need to be more detailed, so are performed by a technician who uses advanced 3D optical and CMM machines. These are able to measure material properties of up to 1/1000th of a millimeter.
The screwdriver range contains around 100 components, which come from mainly European suppliers.
Once a batch of materials has passed quality inspection, they are distributed into storage around the factory. Once an order for a screwdriver has been received, the production line moves into action. It is the picker's job to collect all parts required from the different shelving around the factory. Intelligent storage solutions contain many shelves, but present only the necessary ones just by scanning a barcode. Each step of the production process has its own tray, and once all these are full, they are placed onto roller racking, which takes them to the correct station. The first module to be assembled is the air motor. This is a critical part, as it converts the energy contained in compressed air into a rotary motion, which will turn the screwdriver bit. A worker collects the parts to assemble the air motor from the roller racking. There are three main parts to this module: the bearings, the end plate, and the rotor. The stem of the rotor is positioned over the bearings, and a press forces it into place. The bearings ensure a smooth rotation of the rotor, which maximizes the efficiency of the device. Next, the rotor blades, which catch the pressurized air and generate the rotational force, are slotted into the stem. The casing and end plate can then be placed over the top of this assembly, with a press making sure that all the parts are tightly connected together. Also at this station, the clutch housing is assembled. This will protect the pointy end of the screwdriver, and a plain bearing is added to assist with the rotation of the bit. To translate the rotational force of the motor to a useful rotating speed, the gearbox module is a vital part of the screwdriver. It is made up from a strong metal core, which can take the strain of any load applied to the screwdriver. Small pin bearings are threaded in to designated points around the core by hand. Once secure, the gears are slotted over these pins. The gearbox casing is prepared by pressing a washer into one of the ends, which will reduce friction by maintaining separation between different moving components. Grease is also spread around the interior of the casing to provide lots of lubrication.
Any deviation in the connecting surfaces can affect the air consumption and at the end the performance of the tool.
The gears themselves are then inserted into the casing, completing the gearbox module. The grip is the handle of the screwdriver, which the users will hold whilst operating the tool. It will eventually hold all the component modules, but first it must be prepared. The inside is coated in grease, and seals are placed at every juncture. The trigger, which releases the air pressure causing the turbine to spin, is installed next. A solid metal pin holds this in place, so the trigger cannot come loose. With the seals now in place, the grip undergoes a leakage test. In this test, the screwdriver is connected to a leak detector, which pumps air into the device whilst measuring any fluctuations in the pressure. If the screwdriver can hold this pressure for 10 seconds without leaking, then it passes the test. The pre-assembled modules can now be slotted into their respective places within the grip. First, the components are greased up using several kinds of grease. Then they are connected together and slotted inside the screwdriver grip. The nozzle of the screwdriver is the last component to be added, and it is tightened using a large breaker bar, preventing it from becoming loose. Every part is constantly checked for free rotation, maximizing the efficiency of the device. Now that the tool has been completely assembled, it must be checked. Several tests take place to test the speed and torque the screwdriver delivers.
Today, with the current production setup in the day, 4 operators are able to produce 80 screwdrivers in a shift.
All the tools that pass quality inspection are taken to the packing area, where each screwdriver is cleaned of any grit, grease or oil that may be clinging to the outside. Every tool is checked for scratches, marks or damage. Now the screwdriver can be packaged along with any accessories ordered by the customer. The boxes are then sent off to the shipping team, who will dispatch them to workshops around the world. The pneumatic screwdriver. Truly a wicked invention. Racing cars fly round circuits at incredible speeds. Their lightweight, handling and power partially explain their impressive performance, but something else is a major part of their design. Have you noticed the wings on the cars? These features are to give the car greater downforce, which allows the drivers to corner at faster speeds. So, what is downforce and how does it work? Well, it all starts with exploring how wings can make a plane fly, and the secret is based on something called the Bernoulli principle.
If we take a look at a normal wing on an airplane, what happens is, as the wing moves through the air, the shape of the wing forces the air on top to travel at a faster speed. The Bernoulli effect states that air that's traveling at a faster speed, or any fluid that travels at a faster speed, travels at a lesser pressure. What this means is that the air pressure underneath the wing is greater than the air pressure above it. So the air pressure below pushes up, and the air pressure above effectively sucks the plane upwards, which keeps a plane flying.
So, the greater the speed, the more lift the wing can generate, which is great for planes, but not so desirable for cars, as they could fly off a track and crash. The pioneers in this field were German car manufacturer Opel. In the 1920s, their experimental vehicle research led them to start incorporating wings to some of their car designs that were powered by rockets.
They realized that the rocket-propelled cars needed stability, And so they actually started putting wings on cars at that point in order to achieve stability. At first they were doing 40 miles an hour, and eventually they got up to 120 miles an hour with rocket-propelled cars. But the problem being that they're rockets and they're not particularly suitable for the road, so they were never fully utilised.
The idea of wings on cars seemed to die out with Opel's rocket-fueled research, although in the 1950s, tail wings did start to appear on road cars. But these were more for aesthetic reasons rather than aiding handling. It wasn't until the 1960s that racing car designers started to realise there could be a massive benefit to your lap times if you fitted your speedy racers with a wing. The secret was not to position it like a plane, but to fix the wing to the car upside down. Now, instead of the wing trying to lift the car off the ground, the same Bernoulli effect was pushing the car down onto the tarmac. This technique led to amazing improvements in cornering speeds and lap times, and so the downforce revolution had begun.
In cars or objects that move quite fast, if you're trying to turn a corner at a high speed, you need a lot of friction. Now, friction itself is related to the force down, or the effective mass of a vehicle. If you have no wings, nothing to produce any extra downforce, you only have one mass of your vehicle in order to turn the corner and in order to deal with friction, which is why at high speed a car can skid. If you have downforce, you increase the effective mass of your car by putting a higher pressure down on the ground, which increases the friction and means you can turn a corner at a higher speed because you do not reach the limits of friction.
Today's racing cars will typically have adjustable wings on both the front and rear of the car. These can be modified to allow for independent grip characteristics for both the front and rear tyres, and this creates the ideal handling balance for different driver styles and circuits. Aerodynamics in today's racing cars have become extremely complex as designers discovered that downforce was not just generated by wings, but also by the car itself. The low ride height of racing cars meant that air flowing underneath the car is forced to travel at higher speeds than the air flowing over the top of the body. Additional downforce also comes from the rake, or angle, of the vehicle's body, which directs the underside air up and creates a downward force and increases the pressure on top of the car, like a large wing. Racing with a downforce-equipped car also has an odd characteristic.
The downforce formula basically states that as your speed increases, for every time you double the speed, you quadruple the downforce. What this means is that actually to go around corners in Formula 1 cars, you really have to go faster to get better grip. So if you go from 30 miles an hour to 60 miles an hour and you were able to have downforce, you would double the amount of downforce you have, which means you could go around the corner faster and more effectively at 60 miles an hour than if you were at 30, because you might skid out because you don't have enough downforce in order to generate the pressure and friction on the tyres to go around safely.
So, the faster you enter a corner, the better you will grip and quicker you can get round the circuit. Sounds a simple solution to a dangerous sport, but a modern racing car has many complex details that need to be managed to get the optimum performance on the machine and still avoid disaster.
One of the problems with generating lots of downforce is that if the car gets too close to the road, what can happen is the car will actually graze the road. All of a sudden, the air that's moving along underneath it that is at very low pressure no longer exists. Then that can slow the car down with a sudden and rapid loss of downforce. If this is happening on a corner, this rapid loss of downforce can mean that the driver can skid out unexpectedly and with possible fatal consequences for the driver.
If set up correctly, downforce really is a wicked invention. Can we make a straw fly with just 2 strips of paper? We're going to need a sheet of paper, some sticky tape, a straw, and a pair of scissors. To begin, we take the sheet of paper and cut out 2 strips, one slightly longer than the other. Using the sticky tape to fix the ends, we then create 2 loops out of the paper strips. We take the smaller loop and fix that to what is going to be the front of our aircraft, and fix the larger loop to the rear. So a straw with 2 paper loops, our very own loop plane. Is that really going to fly? We throw our experimental craft into the skies, and it soars through the air as well as a conventional paper plane. We've already seen how Bernoulli's effect explains how aerofoils keep planes in the air or cars on the ground. Well, the same principle applies here. You can think of a loop plane as just a regular plane with the wings folded up. The loop plane behaves almost identically to a regular paper airplane. Here, the air flowing over the bottom edge of the top part of the loops behave like our wing, providing the necessary lift with the combination of the two loops giving our craft stability in the air. The big hoop creates drag or air resistance, which helps keep the straw level, while the smaller loop at the front keeps the plane from turning off course. Can we make a straw fly with just 2 strips of paper? Yes, we can. Wicked challenge smashed. The main aim of a motorcycle helmet is to protect a rider's head at all times, thus preventing or reducing the chances of head injury. But just how were they introduced? Unsurprisingly, the motorcycle helmet closely followed the invention and evolution of the motorcycle itself.
So what we get is faster, bigger bikes designed to work in transport, delivery, they're a mode of communication, and it's really that communication where the evolution of a helmet comes from.
The earliest form of a helmet was the leather caps that were sometimes sold with the motorbikes, but they were too thin and loose to protect the heads of riders. However, it wasn't long until we did see a cry for better protection due to the rise in the number of accidents involving these vehicles.
In 1936, T. Lawrence, Lawrence of Arabia, famously died tragically while trying to avoid 2 boys while riding his motorbike.
A man named Hugh Cairns was the attending physician of this accident. 6 years later, he stated that a helmet may well have saved T.E. Lawrence's life.
Obviously, the case was very high profile, and Cairns started to look into deaths relating to motorcycle dispatch riders, which were traditionally used in the army as means of communication. And Cairns saw that there was a worryingly large amount of head injuries, which could have been avoided. It became mandatory for all military personnel to wear a cork helmet or maybe something like with a rubber lid on the front.
From his findings, he released a case study surrounding the facts and figures with regards to death and injury on motorcycles. At first, not many seemed interested in his findings, but as time passed, the amount of injuries continued to rise.
In 1953, Professor Charles Lombard created the first helmet as we know it today, something which would take the impact of a crash but disperse the energy around it. And Lombard really lobbied to get this as a mandatory safety feature for all bikers.
In the UK, you now must wear a safety helmet that meets the British safety standards whilst riding a motorcycle on the road. From motorsport races to country roads, the motorcycle helmet really is a wicked invention. But just how are they made today? Davida produce timeless, handcrafted motorcycle helmets from their factory in Birkenhead, just over the Mersey River from Liverpool, England.
Davida really started in 1975. Back then, we were a group of engineers making performance parts to improve our motorcycles for the road.
The birth of one of these handcrafted helmets begins with the fiberglass shell. This is produced by hand layering cut sections of fiberglass into a steel mould and coating them in resin. It's then left to set. Once this shell is complete, holes are drilled for the chin strap and goggle strap retainer. This handy jig ensures that the holes are drilled in precisely the right place. The shells still have a raised line running down the centre, caused by the moulding process. This ridge is removed by hand using an orbital sander. The shell is then greased and coated with a special filler used in aircraft technology that will fill even the most minute of scratches and imperfections within the shell. After about 30 minutes of drying time, the shell can then be hand sanded back to a smooth finish so that the filler remains only in these imperfections. Now it's time for a trip to Davida's purpose-built spray booth, where the shell is sprayed with primer. Once the primer has dried and it has been smoothed off again using the orbital sander, it can receive its first base coat colour. Depending on the colour and design of the helmet, it can take several trips to the booth as each layer of paint is built up. In this instance, our helmet is masked up to create a trendy stars and stripes design. This masking process takes immense skill and precision.
Hand masking designs on the shell of a helmet is a real skill. The people I work with are experts in this field and they create amazing work every time.
a special laser-guided center line tool is used to begin the process that will tell the paint master exactly where the dead center of the helmet is, enabling him to create a symmetrical and accurate design. Once he has masked off the helmet, it can receive another coat of paint. If another colour is needed, such as blue in this instance, the helmet will be masked off again and painted once more, and with each step, the design comes to life. Once the design is complete, the helmet will receive a coat of lacquer that is left to dry. Once this is dried, it is once again smoothed down to a mirror-like smoothness with the orbital sander before receiving its final lacquer. This repeated process achieves an amazingly smooth and shiny finish. The helmet is then placed in a light box, where any tiny imperfections in the paintwork can be highlighted and assessed.
What we are looking for in a light box reflection is any distortion of the reflected light. This technique allows us to see imperfections on the surface of the shell.
These are then lightly sanded before being polished. This will leave the shell with flawless paintwork. And with this, the painting of the shell is complete. The interior of the shell can now be created. Firstly, knives that have been specially shaped for each component of the leather part of the helmet are selected. They are then placed onto the leather before a hydraulic press pushes down onto the knife, revealing the cut leather underneath. These knives are a bit like industrial-sized cookie cutters. The next stage of the helmet's birth takes us to the sewing machine. Here, highly skilled sewers will create all of the leather parts of the helmet using the freshly cut leather. This includes leather chin straps, goggle strap retainer, quilted interior lining, and also the cushioned red satin crown. With these components complete, we take a trip to the riveting and popper stud machines. After measuring the depth of the paintwork using this highly accurate gauge, the chin straps and goggle strap retainer are riveted into the painted shell, and popper studs are then attached. The outer rubber trim of the helmet can then be fitted by hand. Once this has been added, the all-important polystyrene shock absorption layer is firmly and carefully pressed and fixed into the helmet.
The dual density shock absorption liner is made from expanded polystyrene. The volume, density and design are critical for the safety of the helmet.
With the EPU liner fitted, the completed, quilted interior is fixed into the helmet. These interiors are built to be interchangeable, giving customers a great choice of trendy looks as they speed along the roads. After a final inspection, the helmet is weighed, and then weight labels are attached, as well as logos, safety certification labels, and other information. The helmet then receives its final polish, and that's it finished. Stylish. All that needs to be done now is to scan the helmet barcode that has tracked its progress throughout production, and final safety labels are attached. It is then bagged and boxed and ready to be sent to a lucky motorcyclist.
Every helmet in our factory is handmade by highly skilled staff.
Motorcycle helmets, a truly classic way to stay safe on the roads. Now that's a wicked invention. So there you have it, a dash through the hidden history, super science and amazing manufacture of products that you use every day but have never realised their amazing backgrounds. Pneumatic drill, downforce and motorbike helmet, all wicked inventions.